All right. Hello, everyone. Welcome to this session today. In today's world, artificial intelligence services and machine learning workloads use up a lot of energy, and they are only becoming bigger and more complex. But even though they use a lot of resources and energy, they are the best tools we have to address the effects of climate change and solve complex business problems. In this session today, our goal is to provide you guidance with the sustainability pillar of the AWS well-architected framework to help you reduce your overall carbon footprint for your AI ML workloads in the cloud. I am Amol Gaikwad, and I am a solutions developer here at AWS. And today I'll be speaking to you about optimizing AI ML workloads for sustainability. In today's session, we'll quickly talk about introductions for cloud sustainability, and then talk about the well-architected machine learning lifecycle. We'll also look at best practices that you can have for optimizing resources for developing, training, and tuning your ML models. We'll also look at different steps you can take to reduce the overall environmental impact of your machine learning workloads while your ML model is in production. Finally, we'll talk about AWS tools and SageMaker capabilities that will help you continuously monitor your ML workload in production and optimize your resources. So when you're building your cloud workloads, the practice of sustainability is to understand the impact that these services and resources you use for implementing your workload have, and to quantify these impacts across each and every phase of your workload lifecycle. Then you can employ best practices and design principles to reduce this impact. And this is cloud sustainability. With that, let's take a quick look at AWS's sustainability journey. AWS has multiple initiatives underway to use water more efficiently to cool our data centers. AWS's data centers are more energy efficient than enterprise data centers due to the comprehensive energy efficiency programs that touch every facet of these facilities. In order to enable customers to reduce their carbon footprint for their workloads in the cloud, AWS also offers Graviton processors, which are much more energy efficient compared to other EC2 instances. You can also use Graviton 3 processors, which gives you 3 times better performance, especially for your machine learning workloads when compared with Graviton 2, the previous version. You can also look at the Amazon Sustainability Data Initiative, which seeks to accelerate sustainability research and innovation by reducing the time and cost that is required to acquire and analyze large sustainability data sets. With these initiatives that you can leverage, you can see that it is certainly more sustainable to build your workloads in the cloud. In fact, a study done by 451 Research suggests that AWS is 3.6 times more energy efficient than the median surveyed enterprise data centers. Not only that, it has 88% lower carbon footprint when performing same tasks compared to these enterprise data centers. Having said that, it's also critical to understand that environmental sustainability is a shared responsibility between AWS and our customers. AWS is responsible for providing you with energy efficient shared infrastructure, sourcing renewable powers and energy, and water stewardship, whereas customers are responsible for optimizing workloads, resource utilization, and reducing the number of resources that are deployed for your workload in the cloud. With this understanding, now let's have a look at the well-architected machine learning lifecycle. The machine learning lifecycle is a cyclic iterative process with defined steps and practices in each phase to create a successful ML workload. Now, when you apply the different pillars of AWS well-architected framework to this machine learning lifecycle, you get the well-architected machine learning lifecycle. Now, we'll dive deeper into each and every phase of the ML lifecycle, focusing on sustainability. Starting with business goal identification. Now, the objective here is to identify the overall environmental impact of your workload. And asking these set of questions will enable you to establish specific sustainability objectives and success criteria that you can measure against in the future. Once you've decided that AI ML is the right tool for your business goals, the next step is to evaluate whether you can build these ML workloads from scratch as a custom model, or can you leverage AWS managed AI services for building these workloads on the cloud. Our AI services portfolio is as shown in this particular slide. You can look at all the different AI services that we have categorized into core and specialized AI services. Using these managed AI services means that you do not need associated resources for collecting, processing and storing your data, and preparing, training, tuning, and deploying your ML models. Now, as an example, you can look at using a machine learning service such as Amazon Monitron for monitoring any abnormalities in your industrial machineries. You can then use this detected data to have preventive measures that can reduce the overall environmental risk due to equipment failures. If in case using AWS AI managed services is not appropriate for your business goal, then you can also evaluate using pre-existing datasets, models, and algorithms. AWS Marketplace offers more than 1,400 ML assets that customers can subscribe to. And using pre-trained models provided by third parties can essentially reduce the resources that you use for data preparation phases and your model training phase. The next step, once you form your ML problem statement, is to choose the appropriate region where you want to implement your workload and host your data. Now, AWS provides information on AWS regions that are closer to Amazon renewable energy projects, and also AWS regions where the grids have low published carbon intensity to host your workload and your data. You can choose the regions based on both your business requirements and your sustainability goals. The next phase in the ML lifecycle is data processing, which entails data collection, data pre-processing, and feature engineering. Now, you can start optimizing resources in data processing by adopting serverless architectures, such as, for example, using AWS Glue and AWS Step Functions for building your data processing pipelines, such as for data ingestion and data pre-processing phases. What this enables you to do is, since these are managed serverless services, you don't have any infrastructure to manage or maintain 24/7. Hence, you're immediately optimizing the resources that are required for your data processing phase. It is also important to consider the file formats that you use while you're looking into your data processing stages. File formats help you reduce the overall storage space that you have for your workload. For example, using Parquet formats compared to CSV formats enhances and reduces rather your storage space. You can also employ compression algorithms to further reduce the space for storing your data. Finally, when looking at different data storage solutions, it's important that you classify your data to understand its significance based on your business outcomes and for your workload. Once you classify the data, you can use that information to determine when you can move the data to a more energy efficient storage tier, or whether you can safely delete the data if it is not required anymore. For example, Amazon S3 gives you energy efficient storage tier for archiving, and you can use this archival storage tier for infrequently accessed data. Another important point here to note is that you do not have to over provision block storage while using SageMaker notebooks for your ML workloads. Rather, you can use object storage solutions such as Amazon S3 for more commonly used datasets. Next, to monitor and quantify improvements, you can use these different metrics that are provided by Amazon S3 Storage Lens. Storage Lens allows you to understand, analyze, and optimize your storage with more than 29 plus usage and activity metrics that it provides you right within the S3 management console, within the dashboard where you can visualize these metrics. You can also use Amazon SageMaker metrics such as disk utilization and storage bytes to make optimal decisions on the type of storage that you use and how you want to scale your storage for your ML workloads. Finally, you can also evaluate whether you can completely eliminate the process of completely eliminate the phase of data processing by using existing publicly available data sets through these data sources, such as the Registry of Open Data on AWS, which also includes the Amazon Sustainability Data Initiative and AWS Data Exchange. Now, when you use these curated data sets, it avoids duplicating the compute and storage resources required for downloading the data from the provider, storing it in the cloud, organizing it, cleaning it, and pre-processing it. These data sources provide you data sets that are similar to the climate data, satellite imagery data, energy data, among others. Now, let's talk about model building, which is the next phase in the ML lifecycle. While building your model, we can start optimizing by first setting acceptable performance criteria. Once you set a performance criteria, then you can choose one of the better energy efficient built-in algorithms that are provided to you to create a baseline model. Once we have this baseline model, you can use multiple other algorithms with increasing complexity to see if your model performance increases or your accuracy increases. You also have the option to combine different models into an ensemble to increase accuracy, but do consider the potential loss of efficiency has a trade-off in this case. Amazon SageMaker experiments help you organize these different trials that you do while building your model, and it also allows you to clean up these training resources right after these trials and experiments complete. While building your deep learning models, it is important that you compile these deep learning models from their higher level language representation to a more hardware optimized instruction set, especially for speeding up the training time required for these deep learning models. Now, you can use any of the open source compilers that are out there, or you can use SageMaker's training compiler to compile your deep learning models, which also speeds up the training for these models. Finally, when building your model, you can also look at different optimization steps by including lifecycle configuration scripts for stopping ideal SageMaker notebook instances and resources. You can also automatically launch training jobs and shut them down once your training job is complete. You can employ MLOps pipelines through various tools and services we have, such as the Amazon SageMaker pipelines, and also use orchestration tools such as step functions for building your MLOps pipelines. The next phase in the ML lifecycle is model training. While training your model, you can start optimizing by first looking at the required resources for training your ML job. Within the SageMaker documentation, we provide recommendations on the various instance types that you can use based on the algorithm that you have chosen. You can also look at CloudWatch metrics that monitor resource utilization for your ML training jobs to right size instance types for your training jobs. Finally, you can also use managed spot instances for taking advantage of unused EC2 capacities for doing your ML training jobs. This way, you reduce the overall impact for unused resources and improve efficiency for your workload. You can also use a debugger to monitor your ML training jobs. A debugger such as the SageMaker debugger allows you to debug, monitor, and profile your training jobs in real time, and it also allows you to optimize resources that are used for your training jobs. It helps in significantly reducing the costs of your training jobs as well by providing you various metrics that you can monitor. The SageMaker debugger also provides you with rules that monitor your workload and will automatically stop a training job when it encounters a bug, which helps you again avoid unnecessary carbon emissions. While tuning and evaluating your model, you can start by using the SageMaker automatic model tuning job for hyperparameter optimization. Now, you can use less compute resources and get better results when you limit your search with fewer parameters and small range of values for your hyperparameter tuning job. And for the search functionality, you can use the Bayesian search, which intelligently guesses the next set of hyperparameters to use based on previous trials and experiments. This enables Bayesian search approach to use 10 times lesser tuning jobs compared to random search while getting an optimal set of hyperparameters for your ML model. Hence, Bayesian search uses 10 times lesser compute resources for your tuning jobs. While conducting multiple hyperparameter tuning jobs in parallel gets work done quickly, however, these tuning jobs only improve with successive iterations and experiments. Hence, typically when you're running one tuning job and using lesser compute resources, you tend to achieve best results and also make your training job much more energy efficient. Last but not least, during model training, you can reduce the storage space that is required for your training logs, for your ML training jobs, and also delete or archive the unnecessary training artifacts while you prepare your model. Finally, we'll look at the next phase in the ML lifecycle, which is model deployment. While deploying your model, it's important to choose the right instance option for your inference environment. For example, for CPU-based inferences, you can use the AWS Graviton 3 processors, which offer you 3 times better performance than the Graviton 2 processors, especially for your ML workloads. While your ML training jobs batch process multiple data streams in parallel, your inference jobs, on the other hand, only process single input data streams in real time. Hence, they use lesser GPU compute resources. So, in these cases, elastic inference allows you to reduce the overall cost and the environmental impact by using GPU compute resources much more efficiently. Finally, for your deep learning models and deep learning workloads, you can certainly use Amazon EC2 Inf1 instances, which are based on the AWS Inferentia chips, which are custom designed for your machine learning workloads. While deploying your model, it is much more sustainable to use a shared inference environment. Rather than deploying a single model behind a single endpoint, it is much more efficient to deploy multiple models behind a single endpoint. A multi-model endpoint is served through a single container. So, you efficiently cut down on your costs as well as the total carbon emissions for your inference jobs. SageMaker handles invocations in a way where it routes the invocations that it gets during an inference job to an instance behind the endpoint, and it then downloads the model from Amazon S3 onto the instance's storage, and finally loads the model from the instance storage to the container's memory to give back the inference results. Now, if the model is already present within the container's memory, the invocation results are much more quicker and faster and efficient. Finally, it is important to also right size your inference environment, and to help you right size your instance types, which you use for your inference endpoints, you can use SageMaker Inference Recommender, which allows you to load test your ML workloads and choose the right instance type for your inference environments. You can look at autoscaling, which helps monitor your endpoints and dynamically adjusts their capacity to maintain steady and predictable performance using as few resources as possible. You can also look at using the Amazon SageMaker Serverless Inference, which helps you spin up resources dynamically and also scales them up and down based on the traffic trends that you receive with your inference endpoint. Now, let's look at Amazon SageMaker Debugger and SageMaker Model Monitor and how they help you monitor your ML workload in production. A machine learning training job can run into various problems, such as vanishing gradients, overfitting, system bottlenecks, which essentially compromise your model performance. Amazon SageMaker Debugger allows you to debug and monitor and profile your training jobs to help resolve such problems and improve your model's compute resource utilization and performance. Debugger also offers tools to send alerts when training anomalies are found and take action against these problems and identify the root cause of them by visualizing the collected metrics and the tensors. And you can visualize them either in SageMaker Studio, or you can download a report for detailed analysis offline. SageMaker Debugger automatically monitors system resource utilizations and metrics for system resources, and it also allows you to customize profile jobs to monitor ML framework metrics in detail. It then correlates these anomalies that it found in resource utilizations with specific processes in your lifecycle. This enables you to quickly find system bottlenecks and resolve them to have much better resource efficiency. You can also visualize system resource utilization metrics such as CPU, GPU, and memory usage right from within SageMaker Studio, or you can certainly download a detailed report from Amazon SageMaker Debugger for offline analysis as well. Machine learning models, while in production, typically make predictions on real-world data, which are certainly not as curated as your training data sets. Now, if the statistical structure of this real-world data set drifts away from the baseline data set that you have used for training your ML model, then you can certainly see a dip in your model accuracy for the predictions. Now, SageMaker Model Monitor enables you to continuously monitor your model and look at different metrics that enable you to take corrective actions, such as retraining your ML model at frequent times when required to maintain your model performance and maintain higher accuracy for your ML models in production. The way that you enable SageMaker Model Monitor is by starting with deploying your trained ML model and enabling data capture on that particular endpoint. So, it captures all the input data streams and the prediction results from your trained model. Then you have the option of creating a ground truth label set for a sample baseline data set, which you can then use to compare against the predictions that your trained model is making. And then you can create a baseline job that helps you, build metrics, and also it suggests constraints for each of these metrics that you can evaluate your model against. Next, you can schedule monitoring jobs that tell you on what type of data to collect, how frequently to collect this data, and what different reports need to be generated. So, for example, you can detect and monitor model quality, model accuracy, bias, and explainability drift. Next, you can visualize these metrics within SageMaker Studio, or you can use your own SageMaker notebooks that you are employing your ML workload in to visualize all these different metrics that are collected within SageMaker Model Monitor. Then you can integrate them with Amazon CloudWatch to send alerts and notifications when there is quality issues that arise, and also timely re-trigger your retraining of the ML model. So, to summarize this session, let's look at a few key takeaways from the session today, and we'll also look at the ML design principles derived from the AWS well-architected framework in order to facilitate a good design for your ML workloads in the cloud. Starting with assigning ownership. What this means is that you apply right skills and right resources to increase productivity. And then you can employ security policies and security standards to systems and services that host your model, your data, and your algorithm. Next, you can enable resiliency by ensuring fault tolerance and recoverability of your ML models through versioning, traceability, and explainability. We spoke about enabling automation through adopting multiple serverless architectures through this session. We also looked at enabling reusability. Here you can also focus on developing independent modular components that can be shared and reused. And of course, we spoke about multiple ways and best practices that you can follow to optimize your resource utilization for your ML workloads. And then finally, enable continuous improvements. You will have to continuously iterate through the metrics that you find while monitoring your ML models and analyze and learn through those metrics to improvise on your resources that you use for your ML model. This is a critical step to reduce resources and hence reduce the overall carbon footprint for your model. That concludes the session. Thank you so much for attending today. If you have any further questions, please feel free to reach out. Thank you.